Hello everyone. Today we are going to move a little bit back and return to chapter 1 where we did not finish last few sections, and that's what we are going to do today. Today we are going to move to section 1.8 and talk about introduction to linear transformations. So I prepared the picture of two sets. Imagine that we have one set, like over here, and we are going to call it domain, and another set we are going to call range. And we are going to build a relation between elements of domain to elements of range. And this relation is going to be called a function in case when for every a here, there is only one f of a here. Remember that function is not supposed to make something like this. Something like this is impossible for the function, right? So every element of domain goes to exactly one element of codomain. Okay? And that's just a little review of what are functions. Now, imagine that domain is not just a set of any objects, but a set of vectors. Imagine that we have a bunch of vectors here. And our codomain or range is not also just like a set of objects, but a set of vectors or vector space. I'm going to label this vector space W and this vector space V. Then function which is making this relation is going to have a special name. It's going to be called a transformation. So I'm going to write down definition of transformation over here. So definition. T is a transformation with domain. And I'm going to just put V and codomain W. And we are going to show it like this. T, the name of the function. And we call it T because it's kind of transformation. And we are going to show which vector space is going to be related to which this one is going to be domain and this one is codomain. I'm going to put here domain and codomain. Okay. Okay. Well, in chapter 1, we mostly were dealing with matrices and just kind of standard vector spaces Rn. So we are going to continue working with these vector spaces. So for this section 1.8, we are going to consider the V and W are like spaces Rn and Rm. Okay, just like for this specific section. Generally speaking, transformation is a function between like any two vector spaces, which is a function, right? But for this chapter section point 1.8, we are going to consider that our V is going to be Rn and our W is going to be Rm. So vector spaces of real vectors with m and n components. I'm going to give a couple of examples. So my example number one. Let's consider a function which transforms R2 into R1. So two-dimensional space into one-dimensional space. I'm going to write down the formula for it. T of x1, x2 two-dimensional space is going to be equal x1 plus x2. Result is going to be just one-dimensional. Numerical example. So transformation of the, let's imagine somebody gives us vector x, which belongs to R2, and this vector x is actually like 1, 2. What is going to be reflection of that vector x? So t of 1, 2, according to my formula, is supposed to be 1 plus 2 or equals 3. And that's going to be that's going to be number, it's going to belong to, you can label it as you like, for example, y. Y is going to be equal to 3, and that's going to belong to R1. Okay. Well, it's not necessary that space is going to just shrink every time you do transformation. You can actually make it bigger. I'm going to give you an example of transformation which is transforming one-dimensional vector space into two-dimensional vector space. So I'm going to give you the formula. T of x1 equals x1, x2, oh, not x2, but x squared. Sorry. So, if you have vector x, which is equal to, for example, 5, and that vector belongs to R1, right? What is going to be transformation of this vector x? That's going to be t of 5, which is going to be 5, 25. And it's going to have two coordinates. Okay? Well, I'm going to write down w, and that's going to be x and x squared, and that's going to be equal 5, 25. So that's not going to be just a number, it's going to be a vector already, right? Okay, in general, guys, what is going to happen? In general, you are going to take a vector from like domain vector space and apply a function to get actually all the coordinates of new vector in codomain, right? And let's imagine that vectors in domain are labeled as x and vectors in codomain are labeled as w. So that's Rn, and I'm going to label Rm here, and we do have a transformation. Well, generally speaking, you are going to have n functions which are going to define those coordinates. So let's consider this w. So w1, the first coordinate of w, is going to be the first function of some coordinates of this vector x, right? The second coordinate is going to be another function. That's function 1, that's function 2 of x1, xn. And I don't know, like the dimension is m, so the last coordinate m, is going to be fm of x1, xn. Okay? And finally, transformation itself of x1, xn is going to be equal a vector of with these coordinates w1, w2, wm. Okay? Well, maybe like I'm going to go back and like tell you what are going to be the functions. For example, let's go to example. Let's consider example 2 again. So what is going to be, for example 2, I'm just going to move a little bit. So what is going to be, this is going to be w1 and this is going to be w2. How my functions are going to look, I'm going to write down that w1 is going to be what? Just x1, and w2 is going to be x1 squared. So actually here the function is just like x, and in this case that's squaring function. So the function f, it's like squaring the coordinate. Now guys, you've probably seen that in this section we are doing introduction to linear transformations. So far we were talking about any transformations. For example, squaring is definitely not linear. But if we stick ourselves to simpler functions, so functions f1, fm, linear functions. If these functions are linear functions, we are going to have linear transformation. What means linear function? Well, for example, let's go back to example number 2. This, for example, is not linear function, x squared, because it's kind of a power of x squared, right? This, the first one, is a linear. So this one is linear, and this one is not linear. We want to deal with linear. Which functions we are going to call linear? I'm going to just literally write them down. So I'm going to write down, so w1 equals, and instead of function f1 of x1, I'm going to just write down like expression for this function. It's going to be some coefficient, linear coefficient, a constant coefficient, multiplied by x1, some another coefficient multiplied by x2, and until we reach the last coordinate. So why is this linear? What we have, it's like an equation of a line. We have first powers of x, right? And we have constant coefficients a11, a12, a1n. And kind of we can have all of these functions linear. And then we are going to have so-called linear transformation. And the last one is mn xn. So this is going to be linear transformation. I'm going to underline it one more time. So in this section 1.8, we are going to deal specifically with linear transformations, not any other like general transformations. Guys, what is nice to see? Well, if you look at this like linear transformation and forget for a second like this part, what you're going to have? You're going to have a column vector here, right? And this one looks a lot like a product of matrix A by a vector x1, xn, right? It's just like you to take the first row of that matrix A and multiply it by x1, xn, the second row. How matrix A is going to look? Matrix A is going to look like this. A11, A12, A1n, lots of other numbers, m1 and amn. Just imagine that you multiply this matrix by this column x1, xn, you are going to get this expression like a linear system, right? And these ones are going to be the column of like right side or resulting vector, okay? So basically, guys, we are going to have something like this. W is going to be equal A multiplied by X. A here is going to be a M by N matrix, and that's going to be matrix transformation. Let me do matrix of transformation. That's going to be better to write down in the beginning. This matrix of transformation can be kind of written slightly different ways. Sometimes people, instead of A, are going to write down T in brackets. And so it's going to mean matrix of transformation. Why do we have T here? Because it's not just any matrix, but it's a transformation matrix. Okay? Let me show you probably example of transformation matrix and then talk a little bit about matrix operators. So let's consider a transformation T, which goes from R3 to R2 and given by next equations. W1 equals 3x1 plus 2x2 plus x3. W2 equals x1 minus 2x2 minus 3x3. So these are equations for transformations. That's how we get new coordinates from all coordinates. New, old. Or like the 3-dimensional vector into 2-dimensional vector. How the matrix of this transformation is going to look? Well, the matrix of this transformation is going to look like, that's the first row, the coefficients 3, 2, 1, right? And that's a second one, 1 minus 2 minus 3. What is going to be the vector which I'm going to transform? 3-dimensional vector. So basically I'm going to write down this transformation as like literally matrix 3, 2, 1, 1 minus 2 minus 3, multiplied by column vector of x1, x2, x3, which has 3 components because we are doing transformation of R3 into R2. And here we are going to have W1, W2, the resulting vector or reflection vector. Okay, and in shorter way, you can write it down like this. W equals AX. So basically, that's just a multiplication by matrix, right? Okay, very good. So now, for example, I'm going to talk about this transformation. And for example, what is going to be the image of vector, I don't know. Imagine that we have vector x, which equals 1, 1, 2. What is going to be the image? Well, we basically either substitute 1, 1, 2 into this system or do this multiplication. Doesn't matter actually. Well, I don't know what is going to be easier because, you know, these are just 3 different ways to write down the same thing, right? I don't know. Okay, I'm going to do actually the system because it's basically the same, right? So I'm going to write down W1 equals 3 by 1 plus 2 by 1 plus 2. W2 equals 1 minus, sorry, I wanted to do eraser, minus 2 by 1 minus 3 by 2. I'm just going to calculate the numbers. So 3 plus 2 plus 2 is going to give me 7, right? 3 plus 4. And 1 minus 2 is minus 1. And minus 6, it looks like it's going to be minus 7, right? So that's the image. You can write down that transformation of vector 1, 1, 2 is going to be equal vector 7, 7. Okay, and again, the result of transformation is called image. And if matrix A, I forgot to mention something about like, if matrix A is a square matrix, we are going to call it matrix operator, which means that you are doing transformation, transformation from Rn to Rn. Well, generally they don't have to have same dimension, but if we do have both spaces of same dimension, we are going to call it a matrix operator. For transformation, we are just going to call it operator. Okay? Now, let's talk about properties of matrix transformations. And I'm going to scroll everything up and write down properties of matrix transformations. TA Rn 2rm. Here, guys, A means that's a transformation which is using a certain matrix A, right? Well, property number 1. What is TA of a 0 vector? Well, we know that any matrix multiplied by 0 is 0. What is transformation of vector multiplied by a scalar? Well, we know that we can take outside of the matrix the scalar and put it just outside, right? Number 3, if we take the sum of two vectors because of the matrix multiplication, you can distribute it onto the first one and onto the second one. This property is called homogeneity. And the second property is called additivity. So actually, matrix transformations are homogeneous and have additivity. You can take a constant from outside of matrix transformation and you can actually distribute transformation over sum of vectors. Well, I can kind of prove some of this because, like, for the first one I told you already, product of the matrix by 0 vector is going to be 0. We proved it somewhere in chapter 1, right? I think I'm going to prove number 3. How about proving number 3? So just maybe verify, because there is not like much of the proof. U plus V is going to be what? Well, we know that this transformation is multiplication of matrix by two vectors. And we know that for matrix multiplication, we can actually do this distribution of a matrix over the vectors. And that's going to be transformation of the first vector plus transformation of the second vector. Kind of obvious, right? Now, linear combination. How transformation affects linear combination? How transformation works with linear combination. Okay, let's see. Imagine that we do have a transformation and we apply it against a linear combination of some vectors with coefficients, I don't know, some n vectors. And again, this n is not related to the dimension of a space. It's just like some vectors. So by homogeneity and additivity, first we can split this sum into C1, U1, and like sum of other transformations. This is additivity applied, right? And then we can apply homogeneity and take the constants outside. And constants and TA U1 plus Cn TA Un. So that's how transformation affects the linear combination. Again, not all transformations affect linear combinations this way, but linear transformation, yes, or matrix transformation, yes, it affects linear combinations this way. So basically, you can apply transformation to vectors and multiply them by the same constant. You probably understand where it goes, right? We already know that we can represent a vector in the basis, and this means that we can transform only the basis vectors and keep the constants if we do transformation. Let's talk about like some special transformations. Zero transformation. Zero transformation is a very weird transformation. It takes any vector and transforms it into a zero vector. What is going to be the matrix of this transformation? The matrix of this transformation is going to be 0, 0, 0, 0, and lots of zeros here. And it's going to have n, it's going to have n columns and m rows, zeros. Zero transformation. Okay, more special transformations. identity transformation. What identity transformation is doing? Identity transformation is taking vector x and returning back vector, same vector, right? What is going to be the matrix? The matrix is going to be identity matrix 1, 1, 1, 0 here, 0 here. Identity transformation is doing transformation from Rn into Rn, just because this one belongs to like has n components and this one has n components, which means that it's not going to be just identity transformation, but rather identity operator, because it's going to transform Rn to Rn, same dimensional space. Okay, now the question is, in general, how to find that matrix of transformation if somebody does not give you equations. Like if somebody gives you equations, you just kind of copy the coefficients and that's going to be the matrix of transformation. But if somebody does not give you equations, how to find transformation matrix? So I'm going to write down how to find matrix of transformation A. To do that, we are going to use standard basis. Use standard which belongs to space Rn. Standard basis consists out of next vectors. Let me remind you, probably you don't remember, that vector e1 has coordinates lots of zeros, vector e2 has coordinates 0, 1, all zeros, and so on. Standard basis. We are going to use this standard basis and to find the matrix transformation. Let's see how it's going to work. So, how it's going to work? Let's imagine that we apply our transformation, which we somebody gives us, to this standard basis. How it's going to work? Well, we remember that transformation is matrix A just applying matrix A over the standard basis vector, right? And how it's going to look? Well, I'm going to write down A1, 1, oh, too many ones, I guess. And 1, A1N, lots of dots, AM1, dots, AMN, right? What is going to happen if I multiply it by this vector? 1, 0, 0, 0, 0. I'm just going to do it once and all others are going to do the same. Well, multiply the first row by this vector. I'm going to get A11 only, because only the first term is going to be, or the first entry is going to be multiplied by 1. The rest are going to be multiplied by 0. Same for the second row, only the first entry is going to be multiplied by 1, the rest multiplied by 0, and until the end. So guys, basically, if I apply transformation on standard basis vector, I'm going to get the first column of my transformation matrix. And if I apply to the second, I'm going to get the second column, and so on. So that's a way to get transformation matrix. Take a standard basis, apply transformation to the vectors of this standard basis, and then combine your matrix of transformation out of like results. So I'm going to write down that matrix of transformation is going to be equal transformation of E1, transformation of E2, and I'm writing them down. Maybe I should write them down as columns. I don't know, like, well, I'm going to just put lots of dots and write down columns in words. I'm going to show you on example how it works. It's better to understand if you see how it works on example. Let's do example. Example. We are going to consider a reflection operator. And that's going to be reflection about y-axis. Why do I call it reflection operator? I'm going to consider two-dimensional space, R2, and that's going to be kind of, image is going to be also two-dimensional space. And how it's going to look graphically. That's x, that's y. Imagine that you are using a vector. That's your x. What is going to be your transformation of that x? That's going to be reflection about y-axis. That's going to be tx, the result. Perfect. What now I'm going to do, guys? I'm going to look at my first standard basis vector, and that's going to be 1, 0. I'm going to draw it. 1, 0. That's going to be my E1. How reflection is going to affect it? Well, reflection about y-axis is going to produce vector like this, right? That's t of E1. What are going to be the coordinates of that vector? The coordinates are going to be -1, 0. So basically, guys, the transformation of E1 is going to give me vector -1, 0. So that's going to be the first column of the matrix. Now E2, my second vector. Let me use a different color. E2. So for E2, which has coordinates what? 0, 1, right? I'm going to draw it. This is E2, right? When we reflected about y-axis, nothing is going to happen just because it's already sitting on y-axis. So I'm going to write down that t of E2 is just going to be 0, 1. It's going to be, well, I don't know, like, let me use a different color. This one. Or no, orange. So in orange, that's going to be t of E2 at the same time. What does it mean, guys? I got the first column, that's the first column, and that's going to be a second column. And I'm going to put them into a matrix. So -1, 0, 0, 1. And that's going to be my transformation matrix. Now I again just take any vector, apply this matrix, and get a reflection. Yeah, I know that in this case reflection is much easier to do without any matrix, but let's apply it to something and see how it works. For example, we use a vector, I don't know, vector x with coordinates -2 and 3. I just picked up two numbers. So what is going to be t of x? I'll need to use matrix -1, 0, 0, 1 and multiply it by vector -2, 3. Let's do what. So first row multiplied by this column is going to be 3 multiplied by 0, and the second row by this column is going to be 3, 2, 3. I'm going to just maybe verify it graphically that it's going to work. So, sorry, need to move a little bit my x-axis. I guess I put it too high. Okay, -2, 3. Let's do this -1, -2, 1, 2, 3. So -2, 3 is supposed to give me a vector looking like this. That's my x. And my resulting vector is 2, 3. 1, 2, 2, 3 is going to give me a vector over here. And yes, this is my t of x. And it looks like it's a reflection, right? Perfect. That's a way we actually find matrix of transformation if somebody does not give us the formula. Somebody just tells you, oh, okay, let's do that. Well, I don't know. I'm going to do maybe one more example of finding the matrix so you can, guys, see like how it works. Or two more examples. Let's do 2 more examples. I'm going to do a projection operator. So it's going to be next example. So guys, what kind of projection is going to be? It's going to be a projection on x-axis. Let me just kind of explain how it works, and then we are going to do the magics. Projection on x-axis. So imagine that we have vector x, and projection is going to produce us vector over here. That's how transformation works. Projection on x-axis. That's x-axis, that's y-axis. How it's going, this transformation is going to work on standard basis. So t of e1, which is going to be t of what? 1, 0, is going to be actually the same vector 1, 0. If you do a projection of the vector along x-axis, which is e1, you are not going to do anything. That's going to be a projection itself. T of e2, which is actually like this vector e2, if you project it on the x-axis, you are going to just get what? 0, 0, 0, 1. The result is going to be 0, 0, because you are going to just project everything along y-axis into one point. So matrix is going to look as 1, 0, my first vector, and then 0, 0, my second vector. That's going to be a projection matrix. Last operator is going to be a rotation operator. Again, why do I call all of them operators? Because they are their relations or transformations between same dimensional spaces, like two-dimensional space into two-dimensional space, or three-dimensional space into three-dimensional space. If you have like a different dimension, either of original space or of the resulting space, they are not going to be operators anymore. Well, I'm going to do rotation. Rotation by angle theta. Well, maybe we just choose a not angle theta, but some specific angle. By angle of 30 degrees. Why don't we do this? That's going to be of 30 degrees. So that's going to be my transformation. First, we're going to draw the picture, how it works, and then kind of try to apply it to our standard basis vectors, x, y here. So for any vector x, the transformation is going to rotate this vector by 30 degrees, and that's going to be the transformation. That's it. The angle is 30 degrees. Now we are going to create a matrix of this transformation. So, well, I'm going to draw like another picture for like standard basis vectors to kind of watch what they do, right? So my standard basis vector e1 is going to be rotated by 30 degrees. So what are going to be the coordinates? T of e1, which is t of 1, 0. Well, the coordinates are going to be, let me increase this picture a little bit, and kind of what is x coordinated, what is y coordinate. Well, that's just a right triangle, right? The x coordinate is going to be, what is length over here? 1 unit, because it was a 1 unit vector, right? So we have hypotenuse multiplied by cosine of 30 degrees, and that's going to be 1 by cosine of 30 degrees, and you guys still remember this, it's a square root of 3 over 2. I'm going to just write down the answer. And y coordinate here is going to be like other side, and that's going to be like 1, the hypotenuse, multiplied by sine of 30 degrees, and that's going to be 1 multiplied by 1/2, and that's going to be 1/2. So I'm going to kind of make it smaller again, move it a little bit, and write down the answer. Answer is going to be square root of 3 over 2x and 1 over 2y. Now I'll need to do a similar operation to my second standard basis vector e2. I'll need to choose a different color, I guess. Otherwise, everything is going to be very messy over here. So my e2, this green one, e2, going to be rotated by 30 degrees. 30 degrees. Let's make it bigger again. So here, guys, we still need to find x and y, right? And x is now going to be here, right? It's still going to be hypotenuse, but the angle over here is going to be 60 degrees. So x here is going to be equal to what? 1 multiplied by cosine of 60 degrees. 60 degrees. And that's going to be 1 multiplied by 1/2, which is 1/2. Y, and by the way, guys, it's going to be negative, right? Because it's like negative direction of x-axis. Maybe I should write down minus starting here, here, and here. I don't have space, but we are going to consider minus 1/2. For y, it's still going to be 1 by sine, and the triangle here is going to be 60 degrees too. And that's going to be 1 multiplied by square root of 3 over 2, which is square root of 3 over 2. So I'm going to write down the answer here, and that's going to be 1/2 with minus in the square root of 3 over 2. And now I'm going to make it smaller again and just write down as a matrix of this transformation. So matrix of this transformation is going to be, first I'm going to write down this vector as a column vector, square root of 3 over 2, 1/2. And then this one, negative 1/2, and a square root of 3 over 2. So this matrix is going to describe rotation by 30 degrees, rotation operator. And in the book, they do it in general. I wanted to show you like a practice how it's going to look, not just in general. Okay, that's all about introduction. And next section, we are going to talk more about like how to combine these transformations and if we do have inverse transformations sometimes. Okay, so see you next section.